Hello there, Mr. Sutton bringing you this lesson on L'Hopital's rule. In this one, we're going to find limits of indeterminate forms specifically by using L'Hopital's rule. Before we try finding limits of indeterminate forms with a new method, let's see if you still remember how to do it the old way. So pause the video and see if you can find this limit right here. Alright, so when we have a limit as x approaches a constant, we usually start by plugging the constant in to see if we get something useful. If we do that in this case, you're going to have, let's see, 4 minus 6 over plus 2, that's 0, over, this is 4 minus 4, also 0. Now, before you go ahead and write equals 0 over 0, please don't do that. We'll explain in a little bit why you should not do that, but here is a mathematically better way of expressing what we have here. We can say that arrow, when we plug 2 into the numerator, we end up with 0. So I'm just going to use an arrow here. I'm not using an equals. I'm saying this implies this. And down here, I'm going to write arrow 2 squared minus 4 equals 0. So I haven't actually written equals 0 over 0. I've just shown that the numerator and the denominator both come out to 0 when you plug in 2. All right, so how do we fix this situation? Because 0 over 0, whether or not we officially write it, is a bad thing. So we can factor and cancel out to get rid of the factors that are causing this 0 over 0. The numerator, we can factor that into x minus 1 and x minus 2. Denominator, we can factor that into x plus 2 and x minus 2. And we see here that we can cancel out these x minus 2's. By the way, this is what was causing the problem. If you plug 2 in, these two factors that we just canceled out both become 0. So that was the issue. Now that we've canceled those out, if we try this limit again by plugging 2 in for x, we end up with, let's see, 2 minus 1 over 2 plus 2, which is 1 over 4. Now just to revisit our pickiness in the beginning in not writing 0 over 0 or equals that, we just found that this limit actually equals 1/4. If we had said up here that this limit equaled 0 over 0, we would basically be saying that 0 over 0 equals 1/4. But it doesn't, right? I mean, we might debate over whether this should be 1 or 0 or undefined. Definitely 1/4 would not be on the list of things that it could be. Now that we've seen the old way of dealing with indeterminate forms, which is basically called algebraic manipulation, let's take a look at the new way of handling these, which is called L'Hopital's rule. So L'Hopital's rule, we're essentially starting out with the limit as x approaches some constant of some fraction, where we can express this as f of x over g of x. So the numerator and denominator, we're basically thinking of those as each being their own separate kind of function. So given this situation, if the limit as x approaches the constant of f and g, if those limits are both 0, so this is kind of like having 0 over 0, but we're not writing it like that. We're writing it like this. So if those are both 0, or if f and g both go to infinity when you take the limit as x approaches the constant, and there's one other condition, the limit as we approach c of the derivative of f over the derivative of g actually exists. So if all these conditions are met, then this limit equals f prime over g prime of x, or at least the limit as x approaches c of that. So let's translate this into English, because there's a lot here. If we get an indeterminate form, so if the numerator and denominator are both 0, or they are both infinity, to deal with this, we differentiate the numerator and the denominator separately, and then try taking the limit again. And we just do that over and over again until we either get a true does not exist or some kind of constant or infinity.
You don't even realize I'm already inside. I'm learning how you speak. I just need to become someone you love.
Both 0 or both infinity. So we're not going to write 0 over 0 or infinity over infinity. But we kind kind of need to know before you go ahead and do this that it's going to come
This
out
winter
to
at
one of
Smugs,
those.
stay 3 nights or
So
more and get
let's do
1
our
night
limit
free.
of our numerator
Smugs is
first.
home to 3
Limit
big
it,
mountains,
as
78
x
trails,
approaches to x
terrain
squared
for all
minus
abilities
3x
with
plus
300 inches of average
just kind of
snowfall.
mentally
Smugs,
plugging two
your
into all
home
these
away from
x's.
home
We
with
still have
daily
4
access to
minus
heated
6
pools,
plus
hot
2,
tubs,
so still
tubing,
0.
Nordic trails, and
Notice
endless
I'm
indoor
showing
play
this
at the
all
Fun
as
Zone
just one
2.0.
Now I'm
Plus,
gonna
enjoy
do
a
the same
variety
thing
of dining
for
and
my
shopping
denominator.
options in the village
Limit
with
as
weekly
x
activities
approaches
to entertain
x
the
squared
entire
minus
family.
4.
Stay 3 nights or
This is
more
going
and
to
get
be
1 night
2
free.
squared
Visit
minus 4,
smugs.com
which is still
today.
0. Now, once I've shown that those are both 0, I'm going to write using L'Hopital's rule. So I'm going to be very explicit about to use it. And then to actually use L'Hopital's rule, we just need to take the limit of the ratio of the derivatives. So what that means basically is differentiate the numerator and the denominator separately, stick it in a fraction,
Hey there,
and keep the
Delilah, what's
limit
it
the
like
same
in New
otherwise.
York City?
So
I'm
what we do need to
1,000 miles
do is we
away,
actually do need to
girl.
rewrite
Tonight
this
you
original
look so
limit.
pretty,
This is part of
yes you
L'Hopital's
do.
rule is showing that this limit equals
Hot
the
square
thing that
can't
we're about
shine
to
as
write
bright
next.
as you.
And so my
swear it's
derivative of my
true.
numerator, that's going to be
Hey there,
2x
Delilah,
minus
don't
3.
you worry about the
And
distance.
notice
I'm
I'm
right
keeping my
there.
limit
If
as
you
x
get
approaches
lonely,
2,
give
so I
this
still have a
song
limit here.
another
And
listen.
now for my
Close your
denominator, that's
eyes.
going to be 2x.
Listen to
And just
my
like
voice,
before,
it's my
I'm going to plug
disguise.
in 2 now.
I'm by
I'm going
your
to mentally check just to
side.
make sure I'm not going to get 0 over 0
Oh,
or
that's what
infinity
you
over
do to
infinity
me.
again. But it looks like I won't. I can see that at least my
Oh, it's
denominator is not
what
going to
you
be
do
0.
to
So I'm plugging
me.
2 into all of those things. We've
Oh,
got
it's what
2
you
times
do to
2
me.
minus 3, which is going to be 1.
Oh, it's what
2
you
times
do
2,
to
which is
me.
4. So this
What
comes
you
out to
do
a
to
final limit of
me.
1/4, which is what we got.
Hey there, Delilah, I know.
All right, let's take a look at another example. Pause the video and give this one a shot. All right, so if we were using correct calculus here, we would start by trying to plug 1 in to see what it would actually come out to. Let's do that and see what we will see. So we've got, let's see here, this is 2 minus 1, which is 1, minus 3 gives us negative 2, and that's going to be over positive 2. So negative 2 over positive 2 comes out to an answer of negative 1. And that's it. That's it. The problem's done. We shouldn't go any further. But some of you might be wondering, like you used L'Hopital's rule on this and you ended up with 3. So you might be wondering, like, why did I get that different answer from doing it just the plug it in way? Well, did you check to make sure that this would give you 0 over 0 before you used L'Hopital's rule? If not, there's your issue. We always need to verify that we have the indeterminate form, one of them, before using L'Hopital's rule. That this rule only works. It's designed for when you get one of those indeterminate forms. If you don't, let's take a look at what might happen. So blindly using L'Hopital's rule without checking first. So this is wrong what I'm about to show you, but it's good to see what happens here. So we have our original limit, and we're going to say, okay, let's take the derivative of this thing. So that's going to be 4x minus 1 all over 1. These are the derivatives of our numerator and denominator. And then plugging 1 into this, we've got 4 times 1 minus 1 over 1. So that's going to be 3 over 1, which comes out to a different answer than what we started with. So this is a kind of a proof that you really do need to verify that indeterminate form first. So this is an example of what not to do. Don't do this. Do what we did up here. Always verify first. So up to this point, we might be wondering why we need L'Hopital's rule. I mean, we're going to plug in whatever x is approaching either way just to see what happens. And on the first problem, we saw there was another way to do it just by simplifying and then plugging in instead of using this new rule. Well, there are some situations where you really do need L'Hopital's rule. This is one where you cannot simplify away whatever is going to happen here. So pause the video and try this one out. All right, so just like before, we're going to take the limit of the numerator and the denominator separately to see what we get. So first, let's do limit of the numerator, sine of x minus 1. So if I plug 1 into this, I'm going to be taking sine of 0, which is 0. Now let me do limit of my denominator, so limit of ln of x as x approaches 1. And if you plug 1 in for x here, the ln of 1 is also 0. So we get 0 and 0, which means we can use L'Hopital's rule. So just like before, let me rewrite my original limit. And what is this going to equal? Well, I've got the limit as x approaches 1 of the derivatives now. So derivative of my numerator, that's going to be cosine of x minus 1. Derivative of the denominator, this is going to be 1 over x. And if we're going to plug in 1, we could do that here, and that would be fine. Another thing you could do in this situation that you don't need to do here, but I want to show it to you just so you know it's an option. You don't actually have to plug things in right away. You are allowed to do any kind of algebraic manipulation you want on this limit before you plug in your number. So you could, for example, multiply by the reciprocal of 1 over x and have like x times cosine of x minus 1 as your new limit so that it's no longer even a fraction. Again, here it wouldn't have made a difference, but sometimes it might if plugging in right away would give you something undefined. So now if we plug 1 in this situation, we've got 1 times the cosine of 0 basically. Cosine of 0 is 1. 1 times 1 gives us a final answer of 1. All right, so here is our final boss battle. We're trying to take the limit as x approaches infinity of e to the x over x squared. In light of what we have just learned, pause the video and give this one a shot. All right, so if we're using the L'Hopital's kind of rule, we try the limit as x approaches infinity of the numerator and denominator. Limit as x approaches infinity of e to the x is just infinity. For x squared, limit as x approaches infinity, that's also growing infinitely. So this is one of those infinity over infinity indeterminates, the first time seeing one of these. So we're allowed to use L'Hopital's rule in this situation now that we've shown this with our limits. So rewriting my original limit here, and now I'll take the derivatives. Derivative of e to the x is e to the x. Still have limit as x approaches infinity. Derivative of x squared is 2x. But now if we take the limit of e to the x, we're still getting infinity. If we take the limit of 2x as x approaches infinity, that's also infinity. So we get the indeterminate form again right after using L'Hopital's rule. Well, not to worry. You can actually keep using L'Hopital's rule if you keep getting the indeterminate form. So using L'Hopital's rule again, and now we're rewriting this e to the x over 2x limit. Again, taking my derivative, I've got e to the x over, now we've got 2. And if I plug infinity in this situation, I no longer have infinity over infinity. It's like infinity over 2, which is infinity. So this is great, but it could take a while. Like this was only x squared. What if this had been like x to the 10th power or the 100th power, right? Do you really want to use L'Hopital's rule 100 times? So don't forget everything you've already learned about the related rates approach. If you have infinite limits especially, you can use that relative rates, basically the faster growing function sort of way of reasoning about this. On this problem, we could have just looked at this in the beginning and said, e to the x is growing faster than x squared. This is a top-heavy function. Therefore, we already know right off the bat that this limit would end up being infinity. And if we had x squared over e to the x, we could say that the limit would come out to 0, again, without doing all this work. So just because we have a shiny new tool here doesn't mean you have to use it on every single problem when an older, more efficient tool will work. So that's it for this one. Hopefully by now you have an inkling of the value and, dare I say it, the limits of using L'Hopital's rule. Until next time, Mr. Sutton signing off.